How are you, my friends? This is Calculus 1, Lecture 12B, and this is a continuation of Lecture number 12, which I will call 12A. Derivatives of hyperbolic functions. In the lecture objectives, we will see the definitions of hyperbolic functions, the hyperbolic identities, and the derivatives of hyperbolic functions. Now, in this slide, we see the definitions of the 6 hyperbolic functions stated very clearly. Now, the first one here we see hyperbolic sine of x is equal e to the power x minus e to the power minus x all divided by 2. And notice there is a minus here. The second one is hyperbolic cosine of x is equal e to the power x plus e to the power minus x all divided by 2, and there is a plus in the hyperbolic cosine. Now the other 4, 3, 4, 5, and 6, we can derive from the first 2. So here we see hyperbolic tangent is equal hyperbolic sine of x divided by hyperbolic cosine of x. You will get this one here, e to the power x minus e to the power minus x all divided by e to the power x plus e to the power minus x. Same idea to get hyperbolic cotan, and hyperbolic secant is the reciprocal of hyperbolic cosine from here. The last one is hyperbolic cosecant of x is equal the reciprocal of hyperbolic sine of x. Now let's look at the graphs of the first 3 functions. This is the graph of hyperbolic sine. See, this is considered the sum of 2 functions, exponential e to the power x divided by 2 plus another function minus e to the power minus x over 2. So we can just take some points here to have the graph, which is in the middle here. This is the graph of hyperbolic sine of x. Now we can see this function is an odd function. So when we have hyperbolic sine of minus x, directly we can write minus hyperbolic sine of x. And also we can see from the graph that the domain is all real numbers. So we can accept any value for x there. And the range also is all real numbers. Now just a little note here. You cannot say this graph is the cubic x cubed. No, it's similar, little similar, but this is hyperbolic sine. If x is positive, we can see here on this side, if x is positive, then hyperbolic sine of x is positive. If x is negative, then the hyperbolic sine of x is negative. You can use these 2 properties in the questions. Now we can see the graph here of the hyperbolic cosine of x. Now this is a sum here of 2 functions also. So this is the graph. It looks like a parabola, but it is not a parabola. This is hyperbolic cosine of x. It's an even function, and we can write hyperbolic cosine of minus x is equal hyperbolic cosine of x. There is no minus there. And also we can see hyperbolic cosine is greater than 0, which is positive for all x, because the range you can see from the graph, it will start from 1 closed to plus infinity. You can say always hyperbolic cosine of x is greater than or equal to 1. So the minimum value is plus 1. It will go up to infinity. Domain, all real numbers. Now these functions, hyperbolic functions, can be used to describe the shape of electrical lines. I will show you now some example. These lines freely hanging between 2 poles. So we can use these hyperbolic cosine functions. Let's look at the last graph here, hyperbolic tangent. In this graph, we have 2 horizontal asymptotes, y equals -1 here down, and y equals +1. Domain will be all real numbers, and the range will be open interval between -1 and 1. Hyperbolic tan also is an odd function. So we can write hyperbolic tan of minus x is equal minus hyperbolic tan of x. If x is positive, then hyperbolic tan is positive on the right side here, we can see. And if x is negative here on the left, then hyperbolic tan will be also negative. Now look at these curves. You can see these in physics. These curves, flexible cable, for example, power line. You see these are power lines on the street, we can see, suspended between 2 points at the same height. See this point and this point here. These curves are called catenary, which is in the form of this equation. Y equals a over 2 times e to the power x over a plus e to the power minus x over a, where a is constant. Now we can see this is hyperbolic cosine. See, they look like parabola, but they are not parabola. So this is called catenary curve. It is the average of the y values of an exponentially increasing. This is increasing exponentially, and this is decreasing exponentially. If you add them, divide by 2, so it will be the average. So this one is hyperbolic cosine. Now, one nice example we can see in real life, the Gateway Arch located in St. Louis City in Missouri, United States, along the Mississippi River. I have visited this place myself. The arch was designed in 1947 and construction began in 1963 and completed in 1965. It looks like a parabola. See here, you could say it looks like a parabola, but it is not a parabola. This one is hyperbolic cosine function. One nice thing you can know about this Gateway Arch is the arch is as tall as it is wide. See, tall here, this is the height, same as the width. It's 190 meters. This one, all this width is equal to the height, 190 meters, which is almost 623 feet. So this is a little application about hyperbolic cosine functions. Now, there is a similarity between the trigonometric functions and hyperbolic functions in some sense, and there's also a little major Now, in this slide, we will see a little comparison between trigonometric and hyperbolic functions. The trigonometric functions are called circular functions because the point cosine of theta, sine of theta lies on the circle x squared plus y squared is equal to 1. And we have the famous formula cosine squared of x plus sine squared of x is equal to 1. Now, on the other side, we have the identity hyperbolic cosine squared of x minus, remember, there's a minus here, hyperbolic sine squared of x is equal to 1. So that means the point hyperbolic cosine of theta and hyperbolic sine of theta, this point lies on the hyperbola of the equation x squared minus y squared is equal to 1. This equation is an hyperbola, and this one is a circle. So this is from where the name hyperbolic came. More about hyperbola, this one here, the equation and the graphs, you can see in the complete pre-calculus course, lecture number 39. Now, a major difference between the trigonometric and hyperbolic functions, when we graph them, the trigonometric functions are periodic, so they repeat every period. The graphs are repeating every period, while the hyperbolic functions are not periodic. So they are just one piece on the graph. We have seen at the beginning the graph of hyperbolic sine, the graph of hyperbolic cosine, and hyperbolic tan. Now, these are some identities you need to know in this lecture. I have mentioned the first two. Hyperbolic sine of minus x is minus hyperbolic sine of x. This is an odd function. Second one is an even function. Hyperbolic cosine of minus x, you can always write it as hyperbolic cosine of x. Now, number three, hyperbolic cosine squared of x minus, remember here there's a minus, hyperbolic sine squared of x is equal to 1. Number four is a little tricky. 1 minus hyperbolic tan squared of x is equal hyperbolic secant squared of x. Number five will be hyperbolic sine of x plus y, hyperbolic sine of x times hyperbolic cosine of y plus hyperbolic cosine of the x times hyperbolic sine of the y. Same formula almost for hyperbolic cosine of x plus y. Also, there should be a plus here. Hyperbolic cosine of x times hyperbolic cosine of y plus hyperbolic sine of x times hyperbolic sine of y. Just remember these nice identities. In this slide, we will see the derivatives of hyperbolic functions. The first two are the most important and easy. The derivative of hyperbolic sine of x will be hyperbolic cosine of x. We can derive that easily. And the derivative of hyperbolic cosine of x will be the hyperbolic sine of x. Remember that. Now, number three will be the derivative of hyperbolic tan will be hyperbolic secant squared of x. And the derivative of hyperbolic cotan of x will be minus hyperbolic secant squared of x. Now you can see number five and number six, you have to memorize these nice, easy formulas. The derivative of hyperbolic secant will be minus hyperbolic secant of x times hyperbolic of tan of x. And the derivative of hyperbolic cosecant of x will be minus hyperbolic cosecant of x times hyperbolic cotan of x. This is the chain rule. Chain rule says if we have the derivative of any hyperbolic function of u, where u is a function of x, then we find the derivative of the whole function, like the derivative of hyperbolic sine of u will be hyperbolic cosine of u times the derivative of u, which is du over dx. And this formula applies for all of them. Now, if we look at example one, we need to show hyperbolic cosine squared of x minus hyperbolic sine squared of x is equal to 1. This is an easy question. Just write on the left side the basic definition of hyperbolic cosine, which is e to the power x plus e to the power minus x all divided by 2. Write the definition of hyperbolic sine of x, e to the power x minus e to the power minus x all divided by 2. Square each one. Here we have to use the formula a plus b squared will be a squared plus 2ab plus b squared divided by 4. There is a minus here. Also, we use the formula for a minus b squared. A squared minus 2ab plus b squared divided by 4. Same denominator, we can add, simplify here, cancel whatever you can cancel. You will left with 4 over 4, which is 1. So this is a correct formula. Example number 2, find the value of the expression, nice question here, hyperbolic sine of ln of 4 plus hyperbolic cosine of ln of 2. So we take this number here and we replace it in the hyperbolic sine. Take this number, ln of 2, replace it in the hyperbolic cosine. It's a nice idea to try before you see the solution, if you like. Now here we see on the right side the definitions. So we apply that. E to the power x, instead of x, we put ln of 4 minus e to the power minus ln of 4 divided by 2. Same thing here, ln of 2 in the hyperbolic cosine. Now from trigonometry, we know e to the power ln of 4 is 4. That's a property. Minus, this is a minus here. e to the power minus ln of 4 is 1 over 4 divided by 2. If you need to see more about logarithmic functions, you can see pre-calculus course. This one will be 2 plus half. This is a half. Take this minus up here. 2 to the power minus 1 will be half divided by 2. Simplify the numbers. The LCD here is 4. 15 over 4 divided by 2 will be 15 over 8. And this is 2 plus half. 5 over 2 divided by 2 will be 5 over 4. The LCD here is 8. Multiply up and down by 2. So you get 25 over 8 is the final answer. This is a nice question also. Let hyperbolic cosine of x is equal to square root of 5 and x is negative. Find the value of hyperbolic cotan of x minus hyperbolic cosine of x all divided by hyperbolic secant of x. This is the same value here, square root of 5. This one we have to find using the formulas, the identities. This one we have to find also. And then we put all the values together to get the final answer. Now we know hyperbolic cosine squared of x minus hyperbolic sine squared of x is equal to 1. So I can put hyperbolic cosine here, square root of 5, square it, it will be 5. Simplify this equation, we get hyperbolic sine plus or minus 2. Now x is negative, that means hyperbolic sine is negative. So we take minus 2 for the value. Hyperbolic cotan will be hyperbolic cosine of x divided by hyperbolic sine of x, which is minus square root of 5 divided by 2. Hyperbolic secant, 1 over hyperbolic cosine, the reciprocal, 1 over square root of 5. Now take all these values on the next slide to find the answer. So we substitute now. Hyperbolic cotan, we have seen minus square root of 5 over 2. There is a minus from the question here. Hyperbolic cosine is square root of 5 over 1. Just make it a fraction. Hyperbolic secant, 1 over square root of 5. You can add here, the LCD is 2. So it will be multiplied by 2 up and down. It will be minus 3 square root of 5 over 2. And here multiplied by the reciprocal, square root of 5 over 1. This will be 5 times 3. So minus 15 over 2 is the final answer. Now example 4, let's find the derivative of the function f of x, hyperbolic cosine of x squared plus 1. In this case, we have to use the chain rule. So f prime will be the derivative of hyperbolic cosine of x squared plus 1 times the derivative of the inside function here, which is x squared plus 1. So the derivative of hyperbolic cosine will be hyperbolic sine of x squared plus 1 times the derivative here, 2x plus 0. So the final answer for the derivative, 2x times hyperbolic sine of x squared plus 1. Another example, really nice. We have a function here, hyperbolic sine squared of 3x. That's the given function. We need the slope of the tangent line to the graph of the given function at the value x equals ln of cube root of 3. Maybe it needs a little calculation here. So let's find the derivative first. Use the chain rule again. The derivative of all this function times the derivative of the inside, 3x. Now, when you find the derivative of this, hyperbolic sine squared, remember, it will be 2. You bring the power here, 2 times hyperbolic sine of 3x times the derivative of the inside, which is the derivative of hyperbolic sine will be hyperbolic cosine of 3x times 3. The derivative of this u. So 3 times 2 will be 6 times hyperbolic sine of 3x times hyperbolic cosine of 3x. This is the derivative. So we need the slope. Slope will be f prime evaluated at this value ln of cube root of 3. So we replace that in the x. So the slope will be 6 times hyperbolic sine of 3, see this is 3 here, x, 3 ln of cube root of 3 times hyperbolic cosine of 3 times ln of cube root of 3. Just a little note here before we start. If you look at 3 ln of cube root of 3, cube root of 3 will be 3 to the power 1/3. So you can bring the 1/3 down. 1/3 times 3 is 1. So all this value is ln of 3. So simply I can take all this value inside the bracket here. That's the little trick. And write it as ln of 3. And this one the same here, ln of 3. Now please go back to example 2 to see how do we do hyperbolic sine of ln of 3 or ln of 4 or ln of 2. So the answer will be 4/3. There is a 6 here from the question. Same idea here, hyperbolic cosine of ln of 3, it will be 5/3. So please do it as we have done in example number 2 in this lecture. So the slope we are after, 40 divided by 3. Now here we have to find the derivative of this function. Y equal ln of hyperbolic sine of x. This is a nice question because we have to use the formula from lecture 12a, which is also lecture 12. We have seen there the derivative of ln of u, 1/u times the derivative of u, or we can say simply u prime over u. This is the derivative of ln of u. So now ln of hyperbolic sine, so ln, this is all u. So the derivative will be u prime over u, which means the derivative of hyperbolic sine of x divided by the same function hyperbolic sine. The derivative of hyperbolic sine is hyperbolic cosine. If you divide hyperbolic cosine of x by hyperbolic sine of x, it will be hyperbolic cotan of x. And this is y prime that we need. Y prime is equal hyperbolic cotan of x. Now, please always check the playlist Calculus 1 solved questions to learn more about any topic like hyperbolic functions, hyperbolic identities, and their derivatives. This is the end of lecture 12b, which is about hyperbolic functions. Thank you for watching. If you like the video, you can subscribe and share it with your friends. I hope I can see you in another video with another topic. Thank you guys for listening.